Hello, my name is Jason Teo and I'm a PhD candidate at UCLA. Today I'll be presenting our work on influence-based provenance for data flow applications with taint propagation. This was a joint effort between myself, Professor Mohammed Ali Gozar, and my advisor, Professor Miriam Kim. This work was done while the second author was a graduate student at UCLA. Today's talk will be focusing on the well-established task of debugging in data-intensive scalable computing. More specifically, how can we debug program outputs that may look wrong or suspicious? To start off, let's consider a short example program. Suppose we have the student grades dataset on the right-hand side with three fields, student ID, course ID, and grades. We want to compute for each department the averages of the best and worst performing classes, so we write the program as follows. First, we compute the grade averages for each course, and then we add a secondary aggregation for the top and bottom averages, where we use the top and bottom two course averages from the previous stage. Now, looking at the output, we notice that the EE record has an abnormally low bottom average of 55. And this seems suspicious to us. So we then ask the question, why is the EE bottom average so low? To investigate this, we can look to the program inputs and try to understand which inputs are causing the program to produce the suspicious output. Since our example is fairly small, it's easy to visually identify that there's a particular record, shown in green here, that is skewing our program output. However, in practice, real-world programs typically don't fit on a single slide, and as a result, we need a way to scale this out and handle debugging with large datasets in data-intensive, scalable computing environments. This brings us to our fundamental objective. How do we identify which inputs are responsible for producing the observed suspicious output or outputs? Within scalable computing, this is far from a new problem. We'll briefly discuss two of the common approaches, DataProvenance and delta debugging, but others are also discussed more in detail in our paper. The first approach is DataProvenance, and this is typically a two-phase process that consists of an instrumentation phase followed by an analysis phase. Instrumentation involves tracking the movement of data through computation operators during an application's normal execution. And the analysis or tracing phase uses this captured information to produce input or output mappings, also known as traces. To illustrate how this might look, recall the previous program. If we were to start with the EE output record, a provenance system might use information collected during instrumentation to trace backwards through the first aggregation operator and identify all the inputs to the EE aggregation key. We can then take these records and continue backwards with our trace to identify all the inputs from the map phase, and so forth, until we eventually reach the original program inputs. You'll notice that data provenance is comprehensive, but it's not quite perfect. In this particular example, almost every input shown on the slide is traced, which brings us to a particular drawback that we seek to address. As demonstrated just now, data provenance systems suffer from a problem of over-approximation. Since they typically rely only on the operator semantics, such as an aggregation or map operator, they tend to neglect UDF semantics, or user-defined functions, and end up tracing extra input records, which in turn can lead to lower precision and extra results that are unnecessary. If we take the previous running example and look at the trace for just the last stage, we see that it traced all of the EE records for the particular EE output. However, in practice, our UDF is special and only requires 4 of the intermediate records at most. As a result, anything else is actually considered irrelevant to the output. And thus, many of the traced records actually have no effect on the final program output that we're interested in debugging. This over-approximation observation is one of the key inspirations for our work, and we'll come back to it later to analyze in more detail. Moving on to our next existing approach, this is going to be delta debugging. Delta debugging uses a provided test function to guide a reduction of the input space that's similar to binary search, and the end result is a minimal set of fault-inducing inputs. The process works as follows. We start with the original program input, and the developer provides a test function. In this case, we define our test function to be, as shown on the screen, with an EE output having a lower value that is less than 60. Now we run the program with the test function on the program outputs, and for the first run, we observe that the test function succeeds, so the suspicious program output behavior is still present. We can then split the input in half and repeat the process, much like a normal binary search. And for our second run, we'll observe that the test function is still succeeding. So we continue to do so, for a third iteration, and finally a fourth iteration. And the end result is a minimal subset of inputs that is able to reproduce the suspicious program output behavior defined by our test function. For this particular example of 11 rows, we found that delta debugging required 3 runs in addition to the original execution. In small or local debugging environments, this is generally fairly acceptable. However, large-scale programs can often take hours or even days to run, and this in turn brings us to the main issue with delta debugging in the domain of large-scale computing. Namely, that rerunning large-scale applications with massive quantities of data can become prohibitively expensive. Combining our observations of the existing approaches, we identified a few key insights that ultimately inspired our work that we'll be discussing today. First, we observed that UDFs can be used to improve the accuracy of our input traces. In particular, we observed that different user-defined functions can have different effects on how inputs and outputs correlate with each other. From delta debugging, we also observed that extra executions in large-scale computing systems can actually be very costly. And finally, we observed that as a side effect of improving precision, we also achieved smaller provenance sizes, which had a nice benefit of reducing overall instrumentation overheads. Based on these insights, we designed FlowDebug. FlowDebug takes as input a Spark program, the target or suspicious outputs that need to be debugged, and optionally a provenance configuration for use in one of our approaches. As output, FlowDebug identifies an input trace, or the individual input records that are most responsible for the suspicious target outputs that were provided as input. FlowDebug is implemented as a library on top of Apache Spark, and it's written in Scala. And it consists primarily of 2 complementary approaches, UDF-aware tainting and influence-based provenance, both of which we will be going into in detail. While both of these can be used in conjunction, they can also be used independently of each other. The first half of FlowDebug, UDF-aware tainting, is based on the following. Earlier, when we looked at the top and bottom average aggregation in our running example, we observed that inputs to UDF don't necessarily contribute to the output. In order to improve the precision of our provenance, we need to track how inputs interact to form UDF outputs. Reusing the running example, we observed that the traditional provenance approach traces all of the EE records, but we also determined that many of the traced records don't contribute to the actual output. To track this kind of UDF behavior, FlowDebug instruments each data object to track operations and interactions with other data objects. The result is a mirrored object API that proxies to the original data object while tracking provenance. Here we have an example of the tainted string class that we implemented to mirror the normal Scala string. And you'll note that its methods behave the same as the original class, but return tainted objects where applicable, and also track an internal provenance state. As for the developer requirements in order to enable this UDF-aware tainting, it's actually fairly small. We demonstrate here that the only required code change is a modification to the data load statement and the Spark context or FlowDebug context that is used for the program. In most cases, Scala's type inference will then automatically adopt the tainted object APIs and no additional developer intervention is required. To give an example of how this looks in practice, we recall that the provenance traits results in most of the inputs which are shown here. If we add UDF-aware tainting, we can specifically debug the 55 value within the EE output record and use it to significantly narrow down the size of our provenance. Many of the relevant records are removed from our trace, and our resulting input trace is actually roughly halved in this particular example. Thus, we find that tracing only the bottom average value can actually significantly improve the trace precision for our tool. While UDF-aware tainting is powerful, it also does have some drawbacks. First, it instruments every data object, and as a result, it actually adds a fairly high computation overhead. Second, there's generally minimal configuration or developer input required. It relies on predefined implementations or for provenance interactions, such as the tainted string class. This also means it's difficult to tailor to every use case. As a result, we decided to also implement influence-based provenance, which is kind of the mirror approach. The key insights behind influence-based provenance are as follows. We wanted to avoid instrumenting every data object so that we don't have any excessive computational overheads. And we also wanted to define a flexible API that can capture differences in input contribution for a particular UDF output. Our approach extends Spark's combined by key API with this object that we call influence functions to define a flexible provenance retention mechanism. Spark's combined by key API is actually the basic building block behind most of Spark's aggregations, including but not limited to the aggregate by key and reduce by key functionalities. The result of extending this API is that we now have a flexible interface for which we've implemented a few common provenance patterns that we've observed and are shown here in the table. In terms of how influence functions themselves are actually implemented, the API there very closely mimics the combiner-like arguments in the combined by key method of Spark. In particular, we implement an init, merge value, and merge function method, as well as an optional post-processing method called finalize to support post-processing functionality that may be implementation dependent. To see influence functions in practice, we can return to our original example. So starting with the provenance-only trace, we applied UDF-aware tainting on the second aggregation to help narrow down our input trace. And now we can apply a bottom one influence function to retain only the input record with the lowest value for each aggregation key in the first stage. And in doing so, we can reduce our provenance even more. This leads us to the main takeaway from influence functions, namely that with proper configuration, influence functions can efficiently improve provenance precision and reduce the number of extra input records being returned. This particular example also demonstrates how influence functions and UDF-aware tainting can be used in conjunction, though once again, this is not strictly a requirement for FlowDebug. An additional benefit of FlowDebug is that we have generally more precise provenance, and as a result of more precise provenance, we also have generally smaller provenance sizes. These smaller sizes typically manifest themselves in terms of lower computation and storage overheads. So our influence-based provenance approach achieves significantly lower overheads than traditional provenance, and our UDF-aware tainting approach, which although it is a little more computationally expensive, still remains fairly manageable despite the overheads that are introduced. Another additional benefit of the reduced provenance that we observed is that FlowDebug is able to pre-compute provenance or input traces during the runtime or instrumentation phase. And as a result, the tracing time is significantly lower compared to other competitors. More of these numbers will be demonstrated in the evaluation, but first I'd like to go ahead and recap the FlowDebug approach. So FlowDebug implements two primary approaches, which is UDF-aware tainting and influence-based provenance. UDF-aware tainting is our implementation to automatically track control and data flow, although it can also come at a slightly higher computation cost. On the other hand, influence-based provenance provides a flexible provenance definition API, but does require a little more developer intervention. And in both cases, we observed that smaller provenance sizes are able to significantly reduce the overhead of instrumentation phase and also enable FlowDebug to conduct extremely fast traces. Moving on to the evaluation, we had three main questions that we wanted to evaluate. First question was, how does our trace accuracy improve when using PerfDebug, or FlowDebug? Our second and third questions focus on performance. What is the instrumentation overhead and analysis time for using FlowDebug? For our evaluations, we compared against two of the existing tools as well as baseline Spark. We compared against Titian, which implements traditional data provenance, and we also compared against BigSift, which implements delta debugging, which is the search-based fault isolation technique we discussed earlier. The programs and datasets we used in our evaluation come from existing literature, and their datasets typically range in between 25 to 50 million records each. For our first question, we were looking at the improvement in provenance accuracy. And we compared against Titian, which implements provenance, and as such we expected to have an overestimation in the provenance size. On the other hand, we also compared against BigSift, which returns a minimal reproducing input set, and thus we expect an under-approximation of the input trace. In practice, we found that FlowDebug achieves 15 to 100% better precision versus Titian, and this is in absolute percentage values. And FlowDebug also achieved 96.8% to 99.3% better recall compared to BigSift. Again, this is also in absolute recall values. For our second question, we also wanted to observe how does FlowDebug's instrumentation overhead compare? And by instrumentation overhead, we mean the overhead of running the original program with FlowDebug as opposed to Titian, BigSift, or Apache Spark. Now we split our results here based on which approaches were being used. Within the programs that used influence functions alone, FlowDebug actually ran 5.4 to 8 times faster than programs instrumented by Titian and BigSift. On the other hand, for UDF-aware tainting, we found that FlowDebug actually added approximately 50% overhead. Now this cost may seem significant, but we'd also like to point out that it includes some of the on-the-fly analysis which is done during our instrumentation phase to reduce our tracing time in the final research question and analysis phase. This is especially valuable because in practice, for a given instrumented run, you can issue several analysis queries to debug multiple outputs, and thus having a well-optimized analysis phase is significantly valuable. Also, as an added effect, this 50% overhead is not as significant as you might initially expect. The overall debugging time, once we factor in the analysis phase for even just a single output, ends up being notably shorter than the other two solutions in Titian and BigSift. For our final evaluation question, we evaluated the tracing or analysis time of FlowDebug. We observed that FlowDebug produces an input trace that is dozens of times faster than Titian and hundreds to thousands of times faster than BigSift. One particularly interesting observation that isn't really clear from this slide alone, unless you combine the results from the previous slide, is that FlowDebug's total trace time is actually a small percentage of the total instrumentation and trace time combined. Now in practice, debugging tools are going to consist of at least one instrumentation phase and one or more trace times. So this means that FlowDebug's trace time of at most 25% is actually going to be lower if you have additional traces. In contrast, Titian's trace time takes roughly the same amount of time as its instrumentation time. And as noted here on this particular screen with the log scale, BigSift takes significantly longer in its tracing phase, again because of its repeated executions in order to isolate a minimal reproducing input subset. In conclusion, I want to recap a little bit about what we've discussed in this presentation. First, we observed that existing input isolation techniques for suspicious outputs are either imprecise in the case of DataProvenance or too expensive in the case of delta debugging for big data analytics programs. We introduced FlowDebug, which implements two particular techniques, UDF-aware tainting and influence-based provenance. And these both were shown in our evaluation to significantly improve the accuracy of the provenance input traces compared to the existing tools of Titian and BigSift. That about wraps it up for my presentation, so thank you for taking the time to watch, and I believe I'll be around later to answer any questions.